Hello and welcome to another Common Core Geometry lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit number 2, Lesson number 6 on congruence and rigid motions. Now, we've been building up the idea of rigid motions for the first 5 lessons, and we've actually done a lot of reasoning already with using rigid motions. Today, though, we're going to formally tie it to the idea of congruence in geometry. So before we make that connection, let's first talk about congruence one more time. Now, you talked a lot about congruence in 8th grade math, or at least that's the theory of it all. That's when it's supposed to come up. And congruence is an interesting idea that really comes up mostly in geometry. So let's take a look at the definition really quickly that you've seen before. Two figures are congruent if they have the same size and shape, if one can be placed exactly on top of another. This is what's called making the figures coincide. Now, the symbol that we use for congruence is this funny looking thing. And it's kind of neat because it's a combination of two different symbols that come from both geometry and from, well, I guess, numbers, right? One of the symbols is this thing, all right? And that's a symbol that really means that two figures have the same shape, or that two figures are what we call similar. And we're going to be getting into similarity a lot later on in the course. Equals, well, you know exactly what the equals means. It's 5 equals 5, 10 equals 10. The equality is really all about the size of the object. Does it have the same lengths? Does it have the same angle measurements, right? Shape is just whether or not I've kind of blown up or reduced the thing. Does it have the same shape? I put the two things together in the congruent symbol. And again, the idea of using the congruent symbol versus the equality symbol is, to a lot of students at this level, very technical, all right? It's completely okay to say something like, 5 equals 5. Because, well, 5 does equal 5, right? That's all right. Maybe a better example would be, it's okay to say 3 plus 2 is equal to 5. But technically speaking, it's really quite strange to say something like line segment AB equals line segment CD. That's a strange thing to say because they're line segments, right? So what would it mean for two line segments to be equal? So instead of doing that, we say that two line segments are congruent. And the idea then is that if I've got, let's say, line segment AB, like this, and line segment CD, and I know they're congruent, then what that means is that I could take this thing and lie it on top of CD, and it would completely cover it and exactly cover it. All right? So the same size and shape, two geometric objects then are congruent. Now let's try to make the connection between congruence and rigid motions. All right, but first an exercise. All right, let's take a look at exercise number 1. The two triangles pictured below are congruent, so I'm telling you that. All right, use tracing paper to verify. What vertices correspond to each other? That's also very important. Make a formal statement about the congruence of the two. Period. All right, so I'm telling you that triangle ABC and EFD are congruent to each other. What I'd like you to do is take a moment and pause the video. Use tracing paper to trace out either one of the triangles. I'm going to go with ABC, so why not stick with that one? And then do whatever you need to do to have it overlap this triangle. Then what we're going to do is we're going to make a very formal congruence statement and we'll put it right into that box. All right, and we'll talk a little bit about that as it goes. But take a little bit of time now to verify that they're congruent. And please do this, it's important. All right, let's take a look. Now, what I've done is I've made a copy of triangle ABC in red. And unlike many times when I've done this, I've actually retained the letters because I want to be able to sort of see where they go. So when I put it over here, even if I do some rotation, it doesn't seem like I'm going to be able to get it to overlap. And that's because, and you probably found this, I need to flip my paper over. All right? And then I need to do a little bit of rotation and a little bit of translation. And I've got them overlapping. They perfectly coincide, so they're congruent. Now, what do we mean by a formal congruence statement? And this is rather important. This is something that it's not just about being picky. This is where, the rubber hits the road and you've got to get it right. So let's take a look. I'm going to say that triangle ABC is congruent to triangle what? Well, what I want to make sure is that when I list the three vertices of the second triangle, I list them so that the first letter I put down corresponds or is in the same place as letter A. That's why I kind of left the letters on the red diagram. So where was letter A? Well, it was right here, and it corresponded to letter E. Then what corresponded to letter B, maybe I'll put it like this so that you can really see it, is letter D, and what corresponded to letter C was letter F. All right? And I specifically wanted to make it so these weren't in alphabetical order like this to kind of challenge, to make sure that you have this. Again, it's important because on occasion I'm going to tell you, triangle ABC is congruent to triangle SRT. And just from that statement alone, you'll know, if I were to rearrange the two triangles and lay them on top of each other, this letter would go with this one. I shouldn't say letter, but this vertex would go with this vertex, this one would go with this one, and this one would go with that one. All right, so this formal statement is very important, and understanding that the order of the letters actually matters, especially on the second triangle. Right? The first triangle, it's like, hey, I could have said ABC, I could have said BAC, I could have said CAB, anything, but then that order dictates the order of those letters. All right, now let's go on and talk about rigid motions, because we've been building them up in this unit. It's part of the unit's title. Let's take a look. So in high school geometry, what we want to do is give a more formal definition of congruence, and let's take a look at that in the box. Two figures in the plane are congruent if a sequence of rigid motions can be found that make the two figures coincide, lie exactly on top of each other. We call this sequence of rigid motions a congruence. All right, that's not maybe so important. What is important is to understand that in high school geometry, you're expected to know that what makes or proves that two figures are congruent from a transformation perspective is whether or not you can find a sequence of rigid motions that maps one of the figures on top of the other. All right? And let's take a look and make sure that we understand this definition by taking a look at this exercise. Exercise number 2. Why does this formal definition of congruent make sense when considering the middle school definition of congruent as same size and shape? So why does this more formal definition make sense now? Take a moment and think about this. All right. Well, this is why. Okay. All rigid motions preserve size and shape. All rigid motions preserve size and shape. We've been talking about that a lot, right? And they preserve size and shape because they preserve distance or length, and they preserve angle measurement. And that's really what gives you the shape, all right? So, all rigid motions preserve size and shape. So, if a sequence of rigid motions, so much writing, a sequence of rigid motions maps one figure onto another, then they must be the same size and shape. All right, and it gives us a nice mathematical way of thinking about congruence other than just, yeah, those two things are the same size and shape. Now the question becomes, can we find some rigid motion that will literally put one of these figures right on top of the other one? All right, we're going to be playing around with this idea a lot in this lesson and the next few, and we're going to keep coming back to it again and again and again. So let's start to get into it. All right, exercise number 3. Let's take a look. In the following diagram, triangle ABC is congruent to triangle DBC. Describe a rigid motion transformation that would map ABC onto DBC. Use tracing paper to help you verify. Explain where each of the vertices on ABC gets mapped to and why. All right. So in this particular problem, we're looking for one of the basic rigid motions that will map triangle ABC onto triangle DBC. The question is, which rigid motion will do it? And we only need one. So think about this a little bit and try to describe it in as much detail as possible. Are you ready? Okay, so when I say something like describe it in as much detail as possible, what I mean is you don't want to just say it's a rotation. You want to say something like it's a rotation around this point by this angle. Now in this problem, it's not a rotation, it's a reflection. So specifically, we're going to, that almost, but not entirely, looks like an E. We're going to reflect triangle ABC in or across segment BC. All right? In other words, we're going to take this red triangle, okay, and we're going to take this red triangle, hopefully, and we're going to flip it across segment BC, okay? And what's going to happen is B maps to B, and C maps to C because they lie on the line of reflection. Okay. And A maps to D. All right. Now, the question says, and this is maybe a little bit premature, why? Why does A map to D? All right. Now, partly it maps to D because the two triangles are congruent. But remember what a reflection is, and let's talk about this just for a moment before we move on, right? If I actually connected point A with point D, right? In order for A to get mapped down to D, what that means is it means that BC, the line of reflection, must be the perpendicular bisector of AD. So actually, let me throw that in here. Because BC is the perpendicular bisector of AD. That does not look like a U. Perpendicular bisector of AD. Now there's nothing, I want to emphasize this, there's nothing in this problem that actually tells us that this is the perpendicular bisector of AD. All right? But because we know these two triangles are congruent, the only way that A gets reflected down to D is if in fact BC is the perpendicular bisector of that. Remember, that's the whole deal with reflections. And quite frankly, reflections might be the most important of all rigid body motions when it comes to mapping one figure onto another. That's debatable, but what I don't want you to forget is other work we've done with reflections where basically the whole idea of a reflection is if we've got a point and we're reflecting it across that line, right, then the whole idea of it is that that's perpendicular and those two lengths are the same. Okay? So just keep that in mind. We're going to get into way more formal sort of proof when it comes to rigid body motions and congruence in future lessons. Today we're just sort of playing around with the idea. All right? Now, one last thing as we move on. The most important thing that we're going to be doing in terms of proving that one figure is congruent to another is with triangles. And the whole idea of proving that two triangles are congruent using rigid body motions is that showing that by using some rigid body motion like a reflection, right, some kind of transformation, then we can map the three vertices of one triangle on top of the three vertices of the other. As long as we do that, the two triangles must be congruent because rigid body motions then will sort of preserve those distances and preserve those line segments. So all we have to do is get those three primary points. And here it's great. These 2 points, B and C, lie on the line of reflection. So when you flip this triangle down, they'll stay there. And then A ends up mapping onto D because BC is that perpendicular bisector of AD. All right, let's keep working with this idea. Let's take a look at exercise number 4. All right. In the diagram below, triangle TRS is congruent to triangle TUV. Give a rigid motion that maps TUV onto TRS. Use tracing paper to verify your transformation. All right. Again, I am looking for just a single rigid body motion, not a combination. We'll get into those in a little bit, but a single rigid body motion that will map TUV, I guess it's this one, TUV onto TRS. Okay? Take a little bit of time now to think about what that would be. Use tracing paper if you need to. Are we ready to go? Let's do it. All right, now remember, we want to be as specific as possible. This time, if we've got triangle TUV outlined in red, a reflection is not going to work, right? If we reflect this thing, let's say, like we did before in VTS or in VT or whatever, it would pop up here. It wouldn't overlay this triangle. So what I'm hoping is that you realize that it was a rotation, all right? And specifically, it's going to be a rotation of triangle TUV about or around point T. If you just said T, you didn't say point T, that's quite okay. About point T by 180 degrees. Let's take a look, right? It's really kind of cool. If I take this and I start to rotate it about point T, what I'll see is that eventually it will land on TRS. Now, as a little side note, how do I know it's 180 degrees? How do I know that it's not 60 degrees or 90 degrees or something like that? And that's an important question. So let's go back to that really quickly. All right. Pay attention just for a minute to this one point, to point U, right? I want point U to get mapped up to point R. I know that right away because U and R are in the same place in that congruence statement, all right? But since U, T, R are collinear, they all fall in a straight line, this is a 180 degree angle, a straight angle. So in order to get U to rotate up to R, the only way I can do that is by rotating that segment a complete 180 degrees. Whoops. That was so much smoother the first time. Right? So we know it's a rotation, and we know it's by 180 degrees. All right, let's keep playing around with this. Okay. Now, when there's only one rigid body motion, and keep in mind those are translations, reflections, and rotations. When there's only one rigid body motion, it's actually pretty simple, right, to think about what it is. When it's more than one rigid body motion, it gets a little bit trickier for a variety of reasons. The biggest one being that there tends to be lots and lots and lots of different ways to do it. So let's take a look at this problem where we need to have more than one rigid body motion. Give a sequence of transformations that would map right triangle MNQ to right triangle WXY. Be as specific as possible in your description of the transformations. There are many correct sequences. Use tracing paper to help visualize them. All right, this one is quite tricky. And I think what I'd like to do is just kind of walk through it together without having you pause the video and kind of work on it on your own. Now again, remember, what I have to do is I've got to get this triangle to be lying exactly on top of this one. It's got to be right on top of this, okay? So one thing I'm definitely going to have to do is I'm going to have to move this triangle. And I tend to move things kind of in physical space, mostly using translations. And what I would always suggest in these sort of situations is that you translate whatever triangle you're trying to map on top of another one. Translate it so that one vertice lies on top of the corresponding vertice. Okay, here's what I mean by that. So I'm going to start with this. Step number one. I'm going to translate triangle MNQ so that N maps to X, like this. Okay? See how that works? I know these two match up with each other. All right, at that point now, technically, this is M prime, Q prime, and N prime. Now we're getting a little bit closer, but we're not quite there, all right? And this is where actually the limits of my technology are a little bit problematic, okay? But what I'd really like to do now is I'd like to rotate this triangle. I think that'll be my next step. I'd like to rotate this triangle so that two sides that are congruent to each other coincide. They're lying on top of each other, all right? Now my prime candidate for that is going to be this side here, rotated so that it matches up with this side here. All right, we literally are going to close this thing up. Now, what I'm going to do, therefore, is that I'm going to rotate triangle M prime, N prime, Q prime about point X by an angle of QXY. It's actually Q prime XY, all right? I really should say I'm going to rotate counterclockwise, right? Oh no, it's actually clockwise, right? So I'm going to rotate this up, rotate it up. Now again, limits of my technology here, I can't actually rotate about point X. I end up rotating it about the center point of the graphical image. But at least with a series of rotations and translations, I can get the same effect. And that will put my triangle just like that. It also means I've got a ton of just terrible stuff hanging out here now. That you can't really see. Ah, much better, right? Much cleaner picture. Now, technically now, we have N double prime, M double prime, and Q double prime. But look at how close we are. And I bet you can figure out what the absolute last transformation is, which is that I've got to flip this triangle across xy. We don't want to use the term flip. What we do want to use is the term reflect. So I'm going to say that I'm going to reflect triangle, we'll say M prime prime, N prime prime, Q prime prime across x, y. And when I do that, again, limits of my own technology, I have to do a bunch of crazy stuff, but I didn't even come close. There we go. The two will coincide. All right, my apologies that I can't really show you that in kind of complete real time. One of the nice things about problems like this is that absolutely, at most, you would have 3 steps, okay, at most. Oftentimes it's only 2, depending on whether or not you really need to have a reflection. In this case, we had to have all of them: a translation, a rotation, and a reflection. Sometimes you'll only need 2 out of the 3. Sometimes, as we saw in previous exercises, only 1. Let me step out of the way though for a second and give you a moment to write down anything that you need to on this slide. All right, let's move on. One last problem. Very often on standardized exams, problems like this, where you're trying to describe a sequence of transformations, rigid body motions, that will map one figure onto another, they have you doing it in the coordinate plane. Because in the coordinate plane, we can be very, very specific about, translate this amount, rotate this amount, reflect across this, right? Because it's all in the coordinate plane. So let's do one problem like that. Exercise number 6. Describe a sequence of transformations that would map triangle ABC onto triangle DEF. Explain why this shows that the triangles are congruent. All right, now again, there's different correct answers here. I just have to somehow get this thing on top of that, all right? Now, it's not likely that I'm going to be able to do it with one transformation alone, all right? I'm gonna have to have a sequence of them. So what I'd like you to do now is pause the video and play around with this for a little bit. All right, let's get to it. Again, many, many different answers, but pretty much all of them will involve just 2 steps: a reflection and a translation, at least in this particular problem. Which one you want to do first versus second is kind of up to you. We could reflect first, translate second, or vice versa. All right, so let's take a look at this triangle, okay? I could easily translate it up and then reflect it across the y-axis. I could also reflect it across the y-axis and then translate it. And I think that's the order I'm going to do it in. I think I'm first, number 1, going to reflect triangle ABC across the y-axis. That's actually easy enough to do. Well, I thought it was. Let's flip this left, right. All right, and it puts our triangle over there. Now notice, it's really in the right orientation now. I've just got to shift it. The question is, how much do I have to shift it? And to do that, it's easy enough, because all you really have to do is pay attention to 2 vertices that are in the same place. All right, now technically at this point, again, keep in mind that this is B prime, A prime, and C prime. So what I'm going to do, whoop, it didn't quite get in the right place. Let me move it to the right spot. There it is. All right, is I'm going to move C prime by 2 units left and 1, 2, 3, 4, 5, 6 units up. All right, so we will translate triangle A prime, B prime, C prime, 2 units left, and did we say 6? units up. And when we do that, 1, 2, 1, 2, 3, 4, 5, 6, we see that the two triangles coincide. Now, the final little piece of this problem is simply, well, how do we know the two triangles are congruent? That's simple enough. Because the transformations were rigid motions, or rigid body motions, either way. You just got to have the word rigid in there. Because the transformations were rigid motions, they didn't change the size or shape of triangle ABC. All right, that's it. Let's take a look. Again, we took that triangle, we reflected it across the y-axis, we then shifted it or translated it 2 units left, 6 units up. Why does this show now that the triangles are congruent? Because we used two things that were rigid motions. If we had used some kind of a transformation like a dilation, which actually changes the size of the object, well, then we couldn't make the claim that they were rigid motions, that they were congruent, because we had brought in a transformation that wasn't a rigid motion. There's lots of other transformations that aren't rigid motions either, but of the 4 primary ones that we've seen, the only one we've seen that wasn't a rigid body motion was the dilation. All right, let's do a wrap-up. In middle school, you learned that congruence is all about objects having the same size and shape. For us, it takes a little bit more of a mathematical bent to it when we say, in order to prove that two things are congruent with transformations, we have to find a sequence of rigid body motions, or just rigid motions, that maps one figure onto another. In terms of triangles, which are the things that we're going to be most concerned about, and eventually we'll understand why triangles are more important than any other type of figure, but in terms of triangles, what that means is that we have to find a rigid body motion that transforms or maps each of the 3 vertices of one triangle onto the 3 vertices of the other triangle. We'll get into that a lot more in the next 2 lessons. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.